we propose a new teleoperation approach using an augmented reality-based interface with haptic feedback that aims to manipulate visually occluded objects with a soft tactile sensor. Our system consists of a haptic device, Franke Mika robot manipulator, an event-based tactile sensor with soft pad, and the second generation of HoloLens headset. Before going further, the problem with teleoperations should be defined first. Sometimes, during manipulation, the operator might lack direct visual information of the manipulator or manipulated object. For such a scenario, we may visualize the robot surrogate, which is a robot model in AR, and move the robot by discovering the environment based on tactile perception. To facilitate the concept, we custom-built an event-based tactile sensor with soft pad to imitate the fingertips. To verify the concept, we conducted two types of experiments. In the first experiment, we benchmarked the approach's efficacy by having a user teleoperate a Franke Mika robot arm in a modified membrane puncture task, in which the goal was to insert one object into a cylinder, incorporating multiple breakable membranes via HoloLens. In the second experiment, participants equipped with HoloLens were asked to perform a series of teleoperating procedures via a haptic device with diverse degrees of visual and haptic feedback. The participants were acoustically isolated to eliminate the effect of audio cues from the haptic device. The primary task in each procedure was to follow sine wave movement for 30 periods in the AR scene by applying effort onto the haptic device. In the first hypothesis, we assume that haptic feedback facilitates motion stopping for cases when a robot rapidly changes its speed during contact with the surface. We discovered that a haptic device indeed gives good information about robot acceleration during penetration experiment. So once the needle pierces the surface, the haptic feedback allows us to hold back the robot immediately, while AR gives visual feedback. To analyze the second part of the experiments, we used statistical analysis, specifically to prove that an AR obstacle does not interfere with the management of a robot. We compared results with a case when there is no obstacle. The center part of the following graph shows that performance with and without obstacles came out to be almost the same. That means that the user is still able to control the robot in a poorly visible environment. Thanks for your attention.